Welcome back. In this video, the objectives are to introduce Gaussian elimination with back substitution. We'll do a sample using Gauss-Jordan elimination, and then we'll solve a system of linear equations using the skills from the previous objectives. So let's take a look at Gaussian elimination with back substitution. In that process, we're going to write an augmented matrix of system of linear equations. And then we'll use elementary row operations to rewrite the augmented matrix in row echelon form. Then we'll write a system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. It will be possible to have no solution. If in the elimination process we obtain a row with zeros except for the last entry, which would be our constant, then you can conclude that the system is inconsistent. So that would look something like this. If we get a bunch of zeros, and then in our final column we get, say, 2. What we're saying there is 0 is equal to 2, which is a false statement. So therefore, it's an inconsistent system with no solution. Gaussian elimination with back substitution is a method that works well for solving systems of linear equations. Using this method, the order in which you do elementary row operations are performed is important. We should operate from left to right by columns using elementary row operations to obtain zeros in all entries directly below the leading ones. So let's take a look at a sample of how that would work. So let's say we've got this system of linear equations. Variables are x, y, and z. So here we have 0x. So we have our coefficients for x, y, z, and w, and then our constant. So we've got our augmented matrix here. And what we want to do is we want to make sure we have a leading 1 and 0. So what we've done is we've just interchanged the first row and the first two rows here. So interchange R1 and R2 so that the first column has leading 1 in the upper left-hand corner. So this might be our original matrix M sub 0, and I'm going to call this second matrix M sub 1, where we've interchanged those. So now what we need to do is we need to eliminate like the 2 and the 4 here in row 3. And we'll also need to do some work with row 4 as well, but we've got to go to work on this row 3 first. It says perform operations on R3 and R4, so the first column has zeros below the leading 1. We're going to take row 1, multiply it by -2, and add it to row 3. So if we multiply row 1 here by -1, or excuse me, by -2, and add it to row 3, I'll have a -2 and a +2, so that's going to become 0. So what would that look like? Rewriting the matrix, I've got 1, 2, -1, 0, and 2, -2, and I multiply that by -2, that row becomes -2, -4, 2, 0, and -4. And then I'm going to add that to row 3, which is just 2, 4, 1, -3, and -2. So when I add those together, my new row becomes 0, 0, 3, -3, and -6. So I perform that operation. -2R1 plus R3 creates this new row. So we're in pretty good shape here. We may recognize a common factor of 3 here. We'll deal with that in just a few minutes. So we've taken care of row 3, so now we need to take care of row 4. We need to eliminate this 1 and this -4. If we take the opposite of row 1 and add it to row 4, okay, because we have equal coefficients here with 1 and 1. If we essentially multiply all this by -1 and add it to row 4, so we have -1, -2, 1, 0, and -2, and add these together, so that becomes 0. That would be -2 and -4 gives us -6. We have +1 and -7 gives us -6. We still add, we get -1, and this was a -2, plus a -19 gives us a -21. So we have done that. So that's good. Now we've got another 0 here. Now we still need to take care of the -6 and -6. Well, if we look here in row 2, we see we have 1 and 1. So if we take row 2 and multiply it by 6, I'll have, this will become 6, and this will become 6, and this will become -12, and this will become -18. And we add these together. 6 and -6 become 0, and 6 and -6 become 0, and -12 and -1 become -13, and -18 and -21 become -39. So we are in better shape than it may appear here. I know these aren't 1s, but now take a look at, in this particular matrix here, take a look at we have 3 and -3 and -6. These are all multiples of 3. So you can see in our instructions below, we're going to take 1/3 of this row. So we multiply all this by 1/3, and we get 1, -1, and -2. And in the bottom row here, row 4, we have -13 and -39. So we're going to multiply all that by -1/13, and we get 1 and 3. So now we've got a really nice matrix here that is in row echelon form. We've got all these 0s and 1s. Our variables are x, y, z, and w, and then our constant. So we can use back substitution here to create the solution to our system. So we know that w is equal to 3. So then using back substitution, we know z minus w equals -2, or z minus 3 equals -2. So z is equal to 1. In our next row here, we see that y plus z minus 2w equals -3. And z is 1. And w is 3. That all equals -3. So I add 5 to both sides. We get y equals 2. And then our top row of our final matrix, we end up with x plus 2y minus z, and then w is 0, equals 2. We solve for x. So x plus 2 times 2 minus 1 equals 2. So we get x plus 3 equals 2, and x equals -1. And we have our solution. Our w is 3, x is -1, y is 2, and z is 1. In Objective 2, we're going to use Gauss-Jordan elimination to solve the systems of equations. We take our system, we can write it into row echelon form, but now rather than using back substitution and apply additional elementary row operations until you obtain a matrix, in reduced row echelon form. So what we want to do is we want to turn all these need to become zeros. If those become zeros, then we're in reduced row echelon form, and it's super easy to find the solution of our system. We've kind of blown back past Gaussian elimination here to obtain row echelon form. Our original matrix here was 1, -2, 3, our augmented matrix, -1, 3, 1, and negative 2, and 2, negative 5. And they just blew right by all the work that it took to get it into row echelon form. So how did we do all that? Well, it takes a little bit of work here, but I first started by just adding these two and creating a new second row. So I just added those together. So my next matrix here, 1, negative 2, 3, 9, if I add those together, I get 0, 1, 4, and 7. And then my bottom row stays the same, 2, negative 5, 5, and 17. Here's the next matrix, M sub 1. Now I need to take care of this 2. So what I did here is I'm going to multiply this second row all by positive 2, and I'm going to add it to row 3. Based on what we saw earlier in the sample, it would be like 2R2 plus R3. So recopying my first two rows here, still have 1, negative 2, 3, and 9. I have 0, 1, 4, and 7. So when I multiply row 2 by 2, that becomes negative 2, that becomes 6, that becomes 2, that becomes negative 4, and I add it to row 3. Negative 2 plus 2 is 0. 6 minus 5 is 1. 2 plus 5 is 7. I feel like I've made a mistake here. And negative 4 and 17 is, that should be positive 13. So I've got a new, so now I need to get this 1 here to become 0. So if I multiply final row here by negative 1 and add it to row 2, if I do that, this becomes negative 1, that becomes negative 7, that becomes negative 13. Rewriting my first row, I get negative 1, or 1, negative 2, 3, 9. My second row also stays the same at 0, 1, 4, and 7. 0 plus 0 is 0. Negative 1 and negative 1 is 0. 4 and negative 7 is negative 3. And 7 and negative 13 is negative 6. Now I'm down to my third matrix here. The negative 3 and negative 6, if I just multiply all that by negative 1/2, I do that get negative 1/2 is negative 1/3 matrix that we have here. So it takes some work to get there. It's not super easy, but it does happen using Gaussian elimination, and our row operations were in row echelon form. So now that we're in row echelon form, we want to make those zeros. We've got the process to do that. If we take our original matrix here, or our fourth matrix really that we've gotten, we need to eliminate the negative 2 and 3. So if we take row 2 and multiply it by negative 2 here, as they're asking us to do, and add it to row 1, right? We multiply this all by 2. The 2 and the negative 2 here are going to drop out. 8 and 3 becomes 11. 14 and 9 becomes 23. So we do get that new row 1 with that 0. But now we need to eliminate the 11 and we need to eliminate the 4. So if we take row 3 and multiply it by negative 11 and add it to row 1, this becomes negative 11 and this becomes negative 22, and we add it to row 1, we do get a new row 1 of 1, 0, 0, and 1. So then all we need to do is to get rid of the 4, and they're telling us multiply row 3 by negative 4. So this becomes negative 4, and that becomes negative 8. and we add those two together, and we get a new row 2 of 0, 1, 0, and -8 and 7 is -1. So we've performed our row operations. We have our variables here of x, y, and z. So we can see that z is equal to 2, y is equal to -1, and x is equal to 1. I think we'll save objective 3 for the next video, but here we have seen how you can use elementary row operations and Gaussian elimination and Gauss-Jordan elimination to easily solve a system of equations. And you'll have plenty of opportunities to get more practice with this when I see you in class.